Hi, my name's Owen Lockwood, and today we'll be talking about the 2021 Physical Review A paper estimating the gradient and higher order derivatives on quantum hardware. The prerequisites for this video are basic knowledge of Qiskit and quantum circuits in addition to introductory multivariable calculus. This paper provides insights, both theoretical and empirical, into gradient-based optimization of quantum variational circuits. First, let's formulate exactly what the problem is. If we have some quantum variational circuit that's a function of parameters theta, we can write it in the following format. The expectation value of some measurement operator m applied on this circuit composed of unitaries that are parametrized by theta. Note that this format is general. This measurement operator could be any Hamiltonian, and these unitary operations could be any. You could have any sort of data re-uploading or any type of circuit within these unitaries. In order to better understand this and focus in on specifically the gradient, we're going to concern ourselves only with a single parameter for now. So note that this theta here is a vector of parameters of size n. But for now, we're going to zoom in on a single parameter. So if we want to differentiate the function f of theta with respect to a single parameter, theta j, where theta j can be anyone, so this is general, we have to rewrite this a little bit. First, let's also zoom in on these unitaries. These are composed of many unparametrized and parametrized gates, where we represent v as unparametrized and u as parametrized. And in this case, we're going to zoom in on a single one of these. We're going to look at an arbitrary operator k on a single unitary, u of j. So now when we want to take the derivative, we're going to focus in on u of k with respect to a specific theta j. Here, k can be represented as the unitary conjugation of a specific one of these. So we have some j and some theta j with this arbitrary operator k and this unitary conjugation. We can also represent this in a much more differentiable friendly format as using more, once again, arbitrary operators a, b, and c, which are independent of this parameter theta j. So we have this format now that only has these cosine and sine dependencies on theta j. At first, this seems trivial to differentiate. We of course know that the derivative of cosine and sine are negative sine and cosine respectively. That is basic calculus. However, in order to actually get this from a quantum circuit, we can't just simply do those operations. We need a more sample-based approach to actually extract this information. So we're going to rewrite this in a format that is friendly to these quantum circuits. Specifically, let's look at the derivative of cosine. We know that the derivative of cosine is equal to negative sine. So if we write this out, where once again we're focusing on a single parameter, this is equal to negative sine. However, we can also write this in the following format, and we'll show exactly how. We can also write it as cosine of theta plus s minus cosine of theta minus s, where s is just some real number all over 2 sine s. Now, how exactly did we get that? Well, we can use some trigonometric identities on the addition of angles to derive that. Specifically, we can show that we know that cosine of theta plus s is equal to, plus or minus in this case, is equal to cosine of theta, cosine of s, minus plus, where this is the reverse, sine of theta, sine of s. And this is just a trigonometric identity. So now we can see if we plug this in over here, so we have cosine of theta, cosine of s, minus cosine of theta, sine of theta sine of s. For this first one, we subtract cosine of theta cosine of s and sine of theta sine of s. And we put this all over 2 sine s. We can see that these will cancel because they're subtracted. We'll get negative 2 sine theta sine s all over 2 sine s. These will cancel, and we'll get exactly what we expected of negative sine of theta. So this is the whole process to just get this derivative of cosine of theta. The same process will apply also to sine of theta, which has a similar angle addition property. We won't derive that here, but the same holds, and simply we replace cosine here with sine, and the derivative is the same. So with this knowledge, we can now focus in and get exactly an equation that uses sampling to get the derivative of k. So now we can say that the derivative of k of theta with respect to theta j is equal to this k operation, because remember this k is just composed of this theta, cosine of theta and sine of theta, and we already just derived those. Theta plus s minus k of theta minus s all over 2 sine s. So now, since we have specified an arbitrary operator and an arbitrary unitary that this is the conjugation of, we can generalize this to our entire function. And we can see that the gradient, or the vector of partial derivatives of f of theta, is simply the application of f of theta plus s minus f of theta minus s all over 2 sine s. And you'll notice there's one thing we want to add to this. Because here this is a vector of parameters, we want to add an ej here and an ej here, where ej is simply the unit vector that is the specific index of this gradient, because this unit vector is going to be all zeros except for a 1 at position j, and we'll repeat this process for every j in the gradient. This right here is what's known as the parameter shift rule. This is a common technique for the analytic gradient of quantum circuits. You'll notice, for those of you familiar with optimization, that this has a lot of similarities in structure to finite difference approaches. However, it's worth noting that this is the analytic gradient, not a numerical estimation. We'll get into those exact differences shortly, but first, let's just note how you can use this technique to get higher order derivatives. We can see that with this formula for f of theta, we can take the second derivative with respect to any theta I, theta j, and simply apply this rule twice, where this is the function, and now we want to take the derivative using this same rule. So we'll get 4 expressions here, and this will be squared. I won't write out the whole equation, but you can see the general format will be f of theta plus s, and now we'll have 2 of these unit vectors, ej, ei, and we'll have all 4 combinations. So it'll be plus plus, minus plus, plus minus, and minus minus. And this will all be over 4 sine squared s, because we applied this twice, so we're multiplying this together. So now that we have a way to take the second derivative, we can clearly compose the Hessian h, also sometimes seen as this gradient squared, which is simply the n by n matrix of partial derivatives with respect to each and every one of these theta i's and j's. This matrix scales with the square of these number of parameters and is often used in optimization because it gives us more insight into exactly how these parameters and the changes of them affect the optimization landscape. Before we get too much into optimization, let's just touch on the differences between parameter shift and finite difference. Up here, we can see the parameter shift rule. And For those of you who don't know, the finite difference rule looks very similar. Specifically, the finite difference rule for taking the derivative at a specific point is f of theta plus h ej, once again, because this is a set of parameters, minus f of theta minus h ej all over 2h. So this is very similar. This top part is exactly the same. The only difference is down here. And we can see that this is a general framework because what the finite difference method is doing is it's taking some function that you want to differentiate, and it assumes between these 2 points, plus h and minus h, that the function is linear. So this assumption is encoded into it, whereas this parameter shift rule has knowledge of the quantum circuit and thus is an unbiased estimate. Specifically, when we're talking about bias, we mean that the bias of an estimator is the difference between the expected value of this estimator and the true gradient. For parameter shift, the scale is on the order of h cubed. For finite difference, this is 0. Sorry, for parameter shift, this is 0. For finite difference, it scales on the order of h cubed. So here we can see that the parameter shift rule and the Hessian are unbiased estimates of the gradient and the Hessian respectively. So now that we've established these differences, let's take a look at the optimization techniques we're going to be using. Specifically, we're going to be looking at traditional gradient descent and Newton's optimizer. Gradient descent, many of you are probably familiar with, as it's a common approach to optimizing neural networks. It is defined as the negative gradient as a step in the direction of the negative gradient of this function. This step size here can be determined either statically or on the fly or using some of the many optimizers such as Atom or RMS prop. Another technique we're going to be looking at is Newton's optimizer, which uses second order information, i.e. the Hessian, to inform our optimization. So we take the Hessian and we invert it, we multiply this by the gradient, and that's our optimization step. This is less common with neural networks because this Hessian, once again, scales n squared, and if we have a billion parameter neural network, that's computationally intractable to handle. However, with quantum circuits, we're often working on the order of 10 to 100 parameters, sometimes 1,000, which makes this a lot more feasible than contemporary neural networks. So now with these optimization rules and the previous knowledge, we'll go into exactly how to implement this in Qiskit and show some empirical results. All right, now let's get into the Qiskit implementation. First, we have to get our standard imports. We have NumPy and Matplotlib as handy assistants, and we have some Qiskit imports, your typical IBM-Q imports, in addition to some more specialized ones from the OpFlow library, which enable us to do gradient and Hessian calculations and effective sampling from circuits. In addition, we import the gradient descent optimizer, which is already built in, so we don't have to write any code to do the formulas that we have previously discussed. First, we generate a simple 5-qubit circuit similar to that in the paper. It has rotations on the x for all 5 qubits, followed by controlled x gates on the following qubits. The single readout operator is on the 3rd qubit, and the identity is applied to all the other ones. So we're just looking at this Z output on a single qubit. So we construct the Hamiltonian, or the measurement output, by saying the identity on every qubit that isn't our target one. Note here that this caret is the tensor product of these operations. We can then get the final readout operator by combining this measurement state function of our readout Hamiltonian and using the @ symbol, which is a composition, with the current circuit state function. We then return this and we can see exactly what the circuit looks like. So here's our Rx gates followed by our C0 gates. Note that when we're using this approach, when we use a simulator, as we will here, the coupling is assumed to be all-to-all, which is not what real hardware is like in most cases. Now, we get into some helper functions for our gradients and expectation calculations. The evaluate expectation and evaluate gradient each take in a parameter vector x and are extremely similar. They simply operate on the measurement operators and the gradient operators. Each one binds the circuit parameters to the specific x values and then evaluates the circuit at these points. Specifically, we use this convert operation to convert a circuit state function into a dictionary or vector state function, which is able to be interfaced with hardware and simulators efficiently. We then return the result of this calculation. For this callback, we keep track of the gradient descent loss at every step so that we can see as the optimizer progresses exactly what's happening inside the circuit. We can then specify exactly how we want to run the circuit. In this example, as I mentioned, we'll be purely simulating it. However, you can also submit this to real hardware if you change the simulate flag to false. Note that this would take a significant amount of time, as for every gradient update, you would have to submit to the queue, and the queue could take a few minutes to a few hours, so this could take a long time to do hundreds of iterations. Now we can get into the main code for generating some of the ideas and figures from the paper. Here we're looking at things that are similar to and inspired by figure 4 of the paper. In this case, we're looking at the effects of the number of shots on the optimization of these circuits. Specifically, we're just trying to minimize that Z measurement operator that we mentioned previously. So we specify an initial random set of parameters. The number of shots we're considering are 10, 100, and 1000. And then we simply have some plotting functionality, which I'm simply going to skip for now. Then for each of these shots, we create the circuit and the measurement operators. We specify these to be a quantum instance with our backend, which in this case is a simulator, and this quantum instance class merely holds all this information together for the backend, for the coupling, for any relevant information, so that we can manage it easily and convert it or submit it easily. In this case, we do convert it to a circuit sampler so that we can get the samples from circuits and do all these calculations. Here we have the gradient, which is already built in Qiskit, and it uses the parameter shift method. We then initialize empty arrays to keep track of our loss function. We create our gradient descent optimizer, specifying a number of hyperparameters that you can change, a max number of iterations of 100, a learning rate of 0.1, and a tolerance of 1 times 10 to the negative fourth. We then actually go and optimize our circuit, specifying what exactly we're minimizing, how we take the gradient, and what our initial point is. We then plot this information. Specifically, we're plotting the number of circuit evaluations versus the circuit expectation. And this second optimization routine, we're specifying a specific initial point, and then we're following the trajectory of these parameters through the landscape of optimization and plotting exactly what that looks like. We then have some graphing functionality, which isn't necessary to go over. It simply creates these outputs to look nice. We'll now run this code. This will take approximately 1 minute to 2 minutes to run. All right, the code has run. Now we can see the results of this code, and on the left side we have a plot of the circuit evaluations versus the expectation value of that measurement operator. Note that the circuit evaluations is a logarithmic plot, and we can see that for the varying number of shots, they all converge to the same point. However, the smoothness of these descents varies widely. We can see 10 shots is an extremely jagged line, whereas 1000 shots is much smoother. This indicates the importance of adaptive shots when we consider optimizations, because although 1000 shots is much smoother, 10 shots converged to the same point. However, it required far fewer circuit evaluations. We can see this exemplified in the trajectory landscape of parameter 1 and parameter 2, as although the 10-shot circuit is very jagged and noisy, it still arrives to the same minimum that both 100 and 1000 shots arrive at. Now we're going to consider some second-order methods, specifically Newton's optimizer. This isn't built in to Qiskit, so we simply write it ourselves. This is very straightforward to do, as remember it's simply the inverse of the Hessian times the gradient. The Hessian and the gradient are both built into Qiskit, so we can create it ourselves. You can also create any optimizer you want very easily in Qiskit using these same building blocks. We specify a number of hyperparameters as before, the learning rates, the shots, and all of the techniques that we use to calculate things. And then we actually bind the parameters as above and perform the optimization. The important thing here is that we are taking the inverse using NumPy of the Hessian and multiplying it by the gradient. Note that we have some regularization here with the identity. This identity regularization makes the Hessian positive. Note that this regularization can be adjusted and changed. Once we have written this optimizer, we can now actually go about applying it. First, we want to specify a circuit that only has 2 parameters. This was done in the paper, so we can focus in solely on a smaller optimization landscape. In this case, we have the exact same circuit. This code is identical to before, except we only have the rotation around the X on the first 2 qubits. We can now run the comparison of optimization techniques. We specify an initial point and a static number of shots, in this case 1000. Note that the creation of the circuit and quantum instance and circuit sampler are the exact same as above. We simply move the code down here. We also use the built-in methods for gradient and Hessian calculations. We once again create the gradient descent optimizer the exact same and optimize it the exact same way as above. This time though, we only run 80 iterations. We then consider our second order minimization, which we wrote the code for in the cell above, which takes in the same information as the traditional gradient descent optimizer and then returns the results. We'll now run this code. Note that this takes slightly longer, as the Hessian is a 2x2 matrix rather than just a gradient, which is only contains 2 values, so it's more computationally expensive. Here we can see that the result is generated showing the Newton's optimizer performing better in terms of the number of circuit evaluations. The reason for this is that even though it requires more circuit evaluations to generate the Hessian, the information that the Hessian contains when informing the optimization procedures is of high quality and important, and ensures that the cost decreases at a much faster rate. So we can see that using second order information can be beneficial even though it's more computationally expensive. Here we expand the example to include all 5 parameters. Note that not all 5 parameters are necessary to achieve the minimum, as was shown in this example. Once again, this optimization routine is exactly the same as the cell above. This time, however, we consider the full 5 parameters. Note that this changes the Hessian from a 2x2 to a 5x5, increasing from 4 parameters to 25. So this will take longer than the previous example. In this case, we are going to specify the initial parameters 0.1 and 0.15 exactly the same as above, simply considering adding on zeros for the other parameters. There we go. Code is done. Now we can see the result of these optimization comparisons, and when we consider the full parameters vector of, in this case, 5 parameters, we can see that the Newton's method does not perform as well as the gradient descent method. This is likely because Newton's method is far more computationally expensive in terms of the number of circuit evaluations, and these additional parameters that we have added are essentially redundant or not essential to getting to the minimum of this circuit. So we're doing more computational calculations for less informative Hessian information. In this case, we can see the importance of choosing your optimizer when you know what exactly your parameters are doing and how the optimizer can potentially speed things up or help your program converge faster. Now we're going to switch and look at a runtime example. Runtimes is a new program released by Qiskit to enable submissions to hardware and cloud devices to run much, much faster. Because previously, as I mentioned, if you wanted to submit to hardware, you would have to wait in queue every time for every job submission. You can now submit one program that is uploaded to the cloud and interacts with simulators or hardware directly and does these optimization loops in a closed job. So you only have to submit it once and you'll get the results once the optimization is done. This can result in significant speedups as you only have to submit one job to the cloud. It's then evaluated and then returned. So to do this, we import runtime and get some runtime message imports here. We have our other standard imports. And then we create some metadata because we're uploading this file to the cloud. In order to do that, we need to specify the name of the program, a description, a max execution time, and these metadatas may be subject to change as this runtimes is still in its early stages. We then also have to specify what parameters and return values we're expecting. They're exactly the same as we previously described. We're giving it some number of shots and we're returning the loss over time. We then also have some interim results. We specify the backend in this case is going to be a simulator. Note that if you simply change this flag to be, in this case, Lima, you could run this on actual hardware. We simply use a simulator for this example. We then upload the program of this actual Python file containing the metadata previously specified. We're going to switch to exactly what this Python file that we're uploading is. We can see that this file looks extremely similar and is almost exactly the same as the previous Jupyter notebook and contains the exact same functions. The only difference is that it's all put inside one main function so that runtime can interact with it easily. Another notable difference is that we have a noise in this simulator. In this case, we're emulating the Bogota quantum hardware, and so we use the coupling maps and the noise models from this device to make our simulator act as similar as possible to the real hardware of Bogota. We can then simply use the same iterations of 10, 100, and 1000 and submit the job each time to be run for these varying inputs, get the results back from the cloud, and then plot them the same as before. We'll now run this. Note that this could take some time as not only are you interfacing with the cloud, you also submit this job in a queue. Now that the results have returned from the cloud, we can see the plot of the circuit evaluations versus cost and the parameter landscape. These plots are the exact same diagrams as shown in the previous notebook, except that they are modeled with the noise from the Bogota hardware. In this case, we can see that each of the shots become much more noisy as it approaches the minimum due to the noise and restrictions of current hardware. Once again, we can see the importance of choosing shots and potentially adaptive shots as 10 shots is still able to converge in much fewer circuit evaluations than 1,000. Once again, we can see the trajectory of these parameters through the landscape. All right, that concludes our discussion. Today we evaluated theoretically and in Qiskit gradient-based approaches to optimizing quantum variational circuits. All of this code will be available below in the description. Thank you. I've been your host today, Owen Lockwood.